So hello again, this is the final instalment of my little whistle-stop tour through the immune system and vaccination, and this is where we're going to start to think a little bit more about microbiology, how our immune system sees things differently, and then some of the main hurdles that we really have when it comes to producing a vaccine. So again, this is just to remind you of where we are in our story, and now we're at part 4, and also to remind you of kind of what we're hoping to achieve during this series of 4 presentations. I know I gave this quotation fairly early on, but I think it deserves to be here again, if I'm honest, that obviously the importance of our immune system is we need to be able to have that ability to mount a destructive response against non-self, so anything that's foreign, anything that's not us, and also an inability, so we sometimes say it's inert, so it basically ignores anything that's host or self. And basically, as we stated at the end of not last time, but the time before, when this fails, and your immune system starts to get confused, you can end up with autoimmunity. And so one of the real hurdles that we have when we're thinking about producing vaccinations is that we need to make sure that there's nothing in that vaccine that our immune system could misinterpret and confuse as part of our own body. I did promise you that we were going to come back a little bit to MHC molecules, and we are. But before we start thinking about the difference between different sorts of pathogens and microbes, I think we just need to think generally about genetic differences between everyone. So it says here, information we already know. Everyone is genetically different. And that must be the case because everyone looks different, which means that our genes must be different inside of us, or we would all look identical. And that's where the unless comes in. So you're genetically different unless you happen to have an identical twin. This doesn't just apply for how we look, it also applies for how our immune system is made up. And the part of our immune system that's different in everyone, so every genetically different individual, is the part that makes up the MHC molecules. So those MHC molecules that present the antigen to the adaptive cells will be slightly different in every single person, unless you have an identical twin. And there's a region of our genetic material, a region of our DNA called the human leukocyte antigen, and the HLA is what encodes, so it gives the genetic material to say how those MHC molecules are made up. And so if your MHC molecules are different from someone else, which they will be, if you put cells, and as we said, MHC molecules are present on everyone's cells because all of your cells could get infected. So every single cell in your body that you could put into someone else will have an MHC molecules on it. So that's essentially a genetic tag saying that they belong to you. Your immune system should ignore your MHC molecules, hopefully. And generally they do. And that's part of the immunotolerance that we spoke about. However, if you then gave some of your cells to someone else, if your MHC molecules are different from theirs, then their immune system will start to destroy it. And this is why for transplants, we need to find what we call a match, or as close a match as possible. And it's that part, the HLA, it's that part of your DNA, of your genetic material, that essentially they're looking for to see if they can find one that's as close as possible. Because if it's different, then as soon as you put those cells, or for example, a kidney or another organ into another person, their immune system is immediately going to think that's non-self and start to destroy it. And the first person to actually perform a successful organ transplant was an American doctor called Dr. Joseph Murray. He actually won the Nobel Prize for this, and he basically transplanted a kidney from the Herrick twins. So there's Ronald and Richard Herrick. You can see here they're identical twins, and basically Ronald was very unwell with kidney failure. Richard gave him a kidney, and he actually did unfortunately have other underlying health issues, but it prolonged his life for over another decade, which is absolutely fantastic. That obviously could only work because genetically they're identical. For people where you don't have someone who's genetically identical, we try to find someone who's close enough, so a match, and then with the use of immunosuppressive drugs and drugs afterwards to try to stop your immune system from destroying the organ, then it sort of hides it enough from the immune system that it can be a successful transplant. So in contrast to that, the cells that make up pathogens are even more different from our human cells. So you could have a friend and you wouldn't ever be able to give them one of your organs because your HLA is too different. Bacteria and viruses don't have HLA, but they produce certain proteins which are so different from our own proteins that, and those are the antigens, that essentially our immune system will definitely recognize it as being non-self. So bacteria, for example, we've got one here, Escherichia coli. So bacteria, their cells are very, very different. So they don't have a nucleus, so they don't have that brain in the cells. And also the proteins that make up their cell membranes are proteins which don't exist in mammals and humans. So as soon as you're infected with a bacterium, that's a red flag to your immune system that that's something that's non-self. One of the problems that we do have with not just vaccine production, but also antibiotic production, is that they can mutate, so they can change. And you've probably heard of some of the what are being called superbugs, which are bacteria which basically we had an antibiotic that killed it, but now it's mutated and it's changed, and now we're struggling to find another antibiotic that can still attack that bacterium. And also because they change so much, again, that makes it quite difficult for us to produce effective vaccines against some of them. On the right hand side here, we've got a virus, and one of the problems that we're going to talk about in a moment with virus production, vaccine production, especially against viruses, is that actually a lot of what makes up a virus, so proteins on the outside of them, the material inside of them that will attack your cells, is made up of DNA and RNA and proteins which are very, very similar to ones that we have in our human cells. So bacteria can survive outside of a cell. A virus actually can't survive and divide and replicate unless it actually infects one of our cells or infects a mammal cell. And basically what it does is it enters into the cell and it basically gets into the brain of our cells and it hijacks the way that our cells work, and it basically steals all the beautiful mechanisms that we have in our cells for itself so that it can replicate and make more of itself. And also another problem, which we touched on when we spoke about the flu vaccines, is that, again, they can change how they look. And so it means that just because you've had a vaccine against it once doesn't necessarily mean that if you're infected with the virus again, the virus won't have changed and that vaccine would still be effective. But as we said, our immune systems recognize that both bacteria and viruses are foreign and mount a strong response against them. But unfortunately, sometimes that response causes a lot of damage to our own cells. And we're seeing that with the current pandemic, that people, even though they've recovered from COVID-19 and now are no longer infected with it, it seems as though there's been so much damage done to especially their respiratory system, so their lungs and also their hearts, that actually they're still going to be suffering and have effects from that for a very long time, possibly forever. And that's not the virus itself that did that. It's the strong immune response that we had that then, as a side effect, has damaged our own cells. So I don't want it to be all doom and gloom. We do want to have some positives coming out of this. So let's think about how we can actually produce effective vaccinations. So I feel as though we need to be an investigator, a bit like Sherlock Holmes. If Sherlock Holmes gave his hand to vaccine production, I think he'd probably find a solution, to be honest. So what we need to think about before you can produce a vaccine is that essentially is there something about the pathogen that definitely looks different from our own cells to our immune system. So as we've said, a lot of bacterium, because they have all those different proteins which don't exist in humans, yes, there's going to be something about that bacterium that is different to us. And so hopefully we'll make our immune system think this is non-self. That would be really, really good. However, sometimes those antigens that we can find that definitely look like non-self won't necessarily provoke that primary response. So we need to make sure that it will promote a primary response, and that then when you come into contact with the actual bacterium or virus, that pathogen again, it will cause a secondary response, which actually means that we will be protected from it. Another problem as well is that just because you found an element that you could potentially use to provoke a primary response, it doesn't necessarily mean it won't cause illness. And that's a problem, because obviously you can't have it that the side effects of a vaccination are so severe that people become unwilling to take it because actually it makes them feel so unwell. You want your vaccination to provoke that primary response but not make people feel particularly unwell. And very importantly, is that something, so that antigen that you've identified in the pathogen, is it something that won't confuse our immune system? So is it something where our immune system won't confuse it for being self and then start to attack our own cells? Like I said in the last part, in a situation that sometimes occurs for people who suffer from MS with certain viral infections. So other difficulties that we do have in vaccine production is everyone is genetically different, as we've already said, unless you have an identical twin. And this obviously also applies, as we've said, to our immune systems. And so that means that actually not everyone's immune system is going to see the same antigen in the same way. So an analogy that I have for this are these two pictures on this slide. So some of you might remember that dress, which was a very big thing on the internet a few years ago, where there were massive arguments as to whether it was black and blue or whether it was gold and white. And essentially, depending on your perception, depending on how you looked at it, you saw it differently. And that's kind of the same concept or same issues that we have with some of our immune responses, that someone's immune response would see it as non-self, attack it, get rid of it, job done. Another person's immune response will also see it as non-self, will attack it, but actually attack it in a different way, and in doing so actually then really damage parts of the body. And this is why it's not just necessarily down to age or underlying health conditions, but this is why different people respond very differently to infections. And this is why some people are getting so unwell with COVID-19, and some other people are actually having very minor symptoms with regards to it. The other picture there, next to the dress, to the left of the dress, is one that I quite like. Depending on how you look at it, some people see a rabbit, some people see a duck, and that's the same kind of thing. Your immune system can see something, it sees it as an animal, well, not an animal, but it sees it as non-self. So everyone's seeing this as an animal, but some people's immune systems would maybe see something as non-self and not a threat. Other people's immune system would see it as non-self and maybe see it as a threat. And again, as I said, some proteins on viruses in particular look too similar to our own that producing a vaccination against it could actually then ultimately lead to widespread autoimmunity, because by vaccinating someone, you're stimulating the immune system to attack that specific antigen. And if that antigen is present in some of our own proteins and things like that, then that's a really bad move. So what about COVID-19? I quite like this cartoon here. So what are your thoughts on the coronavirus? I don't know. It just got viral. I'm not making light of the pandemic. So obviously we want to be able to produce a vaccination against COVID-19. I think that's probably going to be our best way to really curb it. I'm not 100% certain it's going to be going away anytime soon. So for the time being, obviously, follow the government's advice to, work from home if you can, keep yourself as clean as you can, socially distance, and use a face covering. The picture on the right-hand side of this slide actually shows a guy called Ollie Finch. This was quite large in the news just at the start of this year, where they're saying that mumps cases have hit a decade high in England. And part of this is because people think things like mumps, rubella, measles have kind of gone away. But they've only gone away because people are being vaccinated. And this guy, Ollie here, he was on the BBC News, he actually was fully vaccinated, but because so many people weren't, he still contracted mumps. And as you can see, he's got that big swollen face. It's very painful if you have mumps. So please, please, please make sure you have your vaccinations. Please don't depend on the fact that other people will, and then that will necessarily protect you. However, let's hope we do get a vaccination against COVID-19. Obviously, Russia is saying that they have one. Good. But also Oxford University seem to be making quite good strides as well. So that's excellent. I would say the main challenges that we have with regards to production of a vaccination for COVID-19. Firstly, it's an RNA virus. So as we've been saying, it has genetic material in it that looks very, very similar to human genetic material. So we need to be careful that any vaccination that's produced won't confuse our immune systems and we won't end up with autoimmunity afterwards. The other thing is because it's such a new virus, we can't be fully certain how much of a strong adaptive immune response is actually provoked by COVID-19. So we don't know if COVID-19 really causes a very, very strong adaptive immune response in everyone. In some people, it seems to be that actually it's a very, very strong innate immune response. And obviously the problem with this, as we've said, is you can't trick the innate immune response with a vaccine. Your innate immune response is going to work in the same way no matter how many times you come into contact with it. And this comes back to the fact that there's differences in people's genetic makeup, and that includes the genetic makeup of people's immune systems that we don't know. We just don't know fully if actually everyone would actually respond to a vaccine for COVID-19. And it's a bit tricky because there have been reports, haven't there, that people who were infected with COVID-19 have recovered, been declared that they're free from the virus. They should then have had that primary response, which means if they're infected with it again, it should be a very strong secondary response and they shouldn't appear unwell. But that doesn't seem to always be the case in some individuals. So that's a little bit of a concern. But people are really trying, really trying to produce a vaccination. Hopefully we will. I never say anything is impossible. And basically, I would say you don't have to stay home the whole time, but please stay safe. And if you are having to stay home for more often than you need to, try to stay inspired. Keep learning. It doesn't have to be about the immune system, but learning about whatever you're interested in is always a good thing. So that's me fully done. Thank you so much for paying attention. I hope you enjoyed my little sessions. And as I said, you can always email me. My name is still Kate Harvey, and my email address is at the bottom of this slide, kate.harvey@coventry.ac.uk. And maybe one day I'll see you to teach you more about the immune system. Maybe I've inspired some of you enough. Okay, thank you. Bye.